The universe is hiding its greatest secrets in plain sight. We look up at a night sky filled with stars, but that glittering canvas is just the surface of a reality so strange it defies belief. For every answer science provides, a dozen deeper questions emerge from the cosmic shadows. This is a journey to the very edge of understanding, to explore 25 of the most profound and perplexing mysteries of the cosmic horizon. We will dive into the unknown frontiers of space, time, and reality itself, from the invisible forces shaping the cosmos to the bizarre objects passing through our own backyard, all in a fun and relatable style. By the end, you will see the cosmos not as a static picture, but as a living, breathing puzzle waiting to be solved. We will confront the ghostly pull of an unseen super-attractor and grapple with signals from the void that might just be someone saying hello. What part of this hidden universe are you most curious to uncover? Our journey into the cosmic unknown begins with a substance so elusive it has never been seen. It is the most abundant form of matter in the universe, and yet it remains completely invisible to every telescope ever built. This is the mystery of dark matter. Think about that for a moment. Everything you see around you, every planet, every star, every galaxy, all of it accounts for less than 5% of the total content of the cosmos. Dark matter makes up over a quarter of everything that exists. We are the cosmic minority, living in a universe dominated by a ghost. We know it is there because of its gravitational pull. In the 1930s, an astronomer named Fritz Zwicky was studying a giant cluster of galaxies. He calculated how fast individual galaxies were whirling around inside this cluster based on the visible mass of all the stars he could see. The math did not add up. The galaxies were moving far too quickly. There simply was not enough gravitational glue from the visible stars to hold the cluster together. It should have flown apart. Zwicky concluded there must be some unseen mass, some dunkel materie, providing the extra gravity. For decades, this was considered a curious anomaly. Then, in the 1970s, astronomer Vera Rubin provided the definitive proof. She meticulously measured the rotation speeds of stars within spiral galaxies. According to the laws of gravity, stars on the outer edges of a galaxy, far from the bright core, should orbit more slowly, just as Pluto orbits the Sun more slowly than Earth. But Rubin found something astonishing. The stars on the outskirts were orbiting just as fast as those near the center. The only possible explanation was that each galaxy was embedded within a gigantic, invisible halo of matter, a halo that extended far beyond the visible edge of the stars. This halo is dark matter. So what is this stuff? We have a list of things it is not. It is not clouds of normal gas, we would see those. It is not black holes made from regular matter, though some primordial black holes could be a small part of it. The leading idea is that dark matter is made of an entirely new kind of particle, one that does not interact with light or with normal matter in any way except through gravity. It simply passes through our planet and through us as if we were not even there. One candidate is called a weakly interacting massive particle, or a WIMP. As the name suggests, these would be heavy particles that rarely bump into anything. Another candidate is the action, a theoretical particle that is incredibly light but could exist in vast numbers. To find them, scientists have built extraordinary detectors. Some are placed deep in abandoned mines or under mountains, shielded from cosmic rays, waiting for the impossibly rare moment a dark matter particle might bump into an atom in a vat of ultra-pure liquid. Others look to space, hoping to see the indirect signals of dark matter particles colliding and annihilating each other. The presence of this invisible scaffolding is written across the largest structures in the universe. Supercomputer simulations show that without dark matter's gravity to gather normal gas, galaxies like our Milky Way would never have formed. The beautiful cosmic web of filaments and voids, the grand architecture of the cosmos, was woven first by dark matter. We are living in its shadow. We are surrounded by an ocean of ghosts feeling their pull but utterly blind to their form. This is not a minor puzzle, it is a fundamental admission. We do not know what most of the universe is made of, and if that does not send a shiver down your spine, the next mystery certainly will. If dark matter is the invisible scaffold holding the cosmos together, then its counterpart is the unseen force trying to rip it all apart. This is the second and even more baffling mystery of the cosmic horizon, the identity of dark energy. For most of human history, we assumed the universe was static or perhaps slowing down after the Big Bang. The gravity of all that matter, both seen and dark, should be pulling everything back together in a grand cosmic contraction. But in 1998, two independent teams of astronomers made a discovery so shocking it rewrote the rules of reality. They were measuring distant stellar explosions called Type 1 a supernova, which act as cosmic mile markers. By seeing how bright these standard candles appeared from Earth, scientists could calculate precisely how far away they were, and by measuring the redshift of their light, they could determine how fast the universe was expanding when that light was emitted billions of years ago. The expectation was to see the expansion slowing down. Instead, the data screamed the opposite. The most distant supernovae were fainter than they should have been. This meant they were farther away than predicted, which meant the expansion of the universe was not slowing at all. It was speeding up. Something was pushing galaxies apart with ever-increasing force. That something is dark energy. Today, we know this mysterious repulsive force makes up a staggering 68% of the total energy budget of the cosmos. Dark matter is 27%. Everything else, every star, planet, and person, is just 5%. So what could dark energy possibly be? The leading candidate is the simplest and yet most perplexing idea in physics, the cosmological constant. This is a property of empty space itself. Think of the vacuum not as true nothingness, but as a seething quantum foam where particles flicker in and out of existence. This activity gives the vacuum an intrinsic energy, a constant pressure that acts as a kind of anti-gravity. Albert Einstein actually proposed this concept a century ago to force his equations to describe a static universe, later calling it his greatest blunder when the universe was found to be expanding. Ironically, his blunder may be the key to the universe's ultimate fate. But the cosmological constant has a huge problem. The vacuum energy predicted by quantum theory is astronomically stronger, by a factor of 1 followed by 120 zeros, than the gentle push we observe from dark energy. It is the worst mismatch between theory and observation in the history of science. This colossal failure has led physicists to consider more exotic possibilities. Perhaps dark energy is not a constant but a dynamic field that changes over time, a concept sometimes called quintessence. Imagine a fifth fundamental force, one that permeates all of space but whose strength can subtly wax or wane. This idea opens up terrifying possibilities for the far future. If the repulsive push of dark energy remains constant, the universe will expand forever, galaxies flying apart until the sky goes dark and cold in a heat death. But if dark energy's strength increases, a scenario known as phantom dark energy, the outcome is far more dramatic and violent, the Big Rip. In this scenario, the repulsive force grows so powerful it overcomes every binding force in nature. First, galaxy clusters will be torn apart, then individual galaxies. As the end approaches, the force would rip stars from their galaxies, planets from their stars. In the final moments, it would overcome the forces holding atoms together, and then the very fabric of spacetime itself would be shredded. The universe would end not with a whimper, but with a catastrophic, instantaneous tear. Dark energy is the dominant player in our cosmic story, a story we have only just begun to read. we are left with a universe where the two most powerful ingredients are complete enigmas, one pulling, one pushing, locked in a battle that will decide the fate of everything. The silence is the loudest sound in the universe. We live in a galaxy with hundreds of billions of stars, most likely orbited by trillions of planets. The universe itself is nearly 14 billion years old, providing more than enough time for intelligence to arise, spread, and flourish. Given these staggering numbers, the cosmos should be teeming with life, buzzing with the chatter of countless civilizations. Yet when we point our radio telescopes to the heavens, we hear nothing but a profound and unsettling quiet. This glaring contradiction is the Fermi paradox, named for physicist Enrico Fermi, who famously asked over lunch one day, "Where is everybody?" It is a question that haunts every search for extraterrestrial intelligence. The math seems overwhelmingly on the side of life. Scientists like Frank Drake tried to quantify this optimism with an equation. The Drake equation multiplies a series of probabilities: the rate of star formation, the fraction of stars with planets, the number of those planets in the habitable zone, the fraction where life actually emerges, the fraction where life becomes intelligent, and the fraction that develops technology capable of broadcasting its existence. Even when we plug in extremely conservative estimates, the result suggests there should be many civilizations out there. So why do we see no signs of them? Why have we not found any artifacts, any signals, any megastructures? One of the most sobering answers is the concept of the Great Filter. This theory suggests that somewhere between the emergence of non-living chemistry and the rise of a galaxy-spanning civilization, there exists a step, a barrier that is extraordinarily difficult to pass. It is a cosmic bottleneck. The terrifying part is we do not know if this filter is behind us or still ahead of us. If the filter is behind us, it means the step from simple life to complex, intelligent life is incredibly rare. Perhaps the jump from single-celled organisms to multicellular life took a unique, miraculous event on Earth. In this scenario, the universe might be filled with microbial slime, but silent of song and symphony. We got lucky, but if the Great Filter is still ahead of us, the implications are far darker. It would mean that the step from a technological civilization like ours to an interstellar one is almost impossible. Perhaps every advanced culture inevitably destroys itself with its own technology, through war, environmental collapse, or a runaway artificial intelligence. Or perhaps they encounter something out there, something that snuffs out civilizations before they can spread. We would be naive, broadcasting our location into a silent and dangerous forest. Other solutions to the paradox are less grim, but no less strange. Maybe advanced civilizations are simply nothing like we imagine. Their technology, their communication, their very existence might be so alien that we are looking right at it without understanding what we are seeing. They might use neutrino communication or exist as uploaded consciousness in simulated realities with no interest in physical starships. Or perhaps there is a galactic rule, a prime directive of sorts, where older civilizations observe younger ones like ours from a distance, waiting for us to reach a certain maturity before making contact. They see our wars, our struggles, and decide to stay quiet. Then there is the possibility of cosmic archaeology. Maybe they were here and they left traces we have not yet recognized. Some scientists scan star systems for signs of Dyson spheres, hypothetical megastructures built around a star to capture its entire energy output. A star dimming in an unusual, unnatural pattern could be such a sign. Others look for probes that might have visited our solar system long ago. The silence is not empty, it is full of questions. Are we alone, the first or the last? The answer to the Fermi paradox will tell us not just about the universe, but about our own future. It forces us to look at our fragile planet and wonder if our voice will one day join a chorus, or if it will be the only one ever sung. And if the stars are silent by design, what are they hiding from? Amid the cosmic silence, the universe occasionally screams. These are not the slow, steady radio songs of stars or the gentle hum of the cosmic microwave background. These are sudden, violent shrieks, blasts of energy so intense they can outshine an entire galaxy for a fraction of a second. They are called fast radio bursts, and they are one of the most urgent puzzles in modern astronomy. The story begins in 2007 when astronomer Duncan Lorimer was reviewing old data from the Parkes Radio Telescope in Australia. Buried in the observations was a single, colossal spike of radio waves that lasted just 5 milliseconds. It came from deep space far beyond our galaxy. The signal was so powerful and so brief that for years many wondered if it was just a glitch, some earthly interference. But then more were found. Today we have detected hundreds of these bursts, each one a flash of mystery arriving from billions of light years away. Imagine the energy required. In that fleeting millisecond, a single fast radio burst can release more energy than our sun puts out in 80 years. And then, just as suddenly as it appeared, it is gone. The first and greatest challenge is finding where they come from. Pinpointing the origin of a flash that lasts less time than the blink of an eye is a monumental task. It requires networks of radio telescopes across the globe acting as one giant ear, snapping to attention at the moment of the blast. Through this incredible coordination, astronomers have traced many bursts back to distant galaxies, often small, turbulent, or star-forming galaxies. But in a stunning twist, in 2020, we detected one coming from inside our own Milky Way. This nearby burst was a gift because for the first time we could identify the culprit. It originated from a magnetar, a type of neutron star with a magnetic field so powerful it could wipe a credit card from half the distance to the moon. Magnetars are born in the supernova explosions of massive stars, and they are cosmic powerhouses capable of colossal starquakes and magnetic explosions. This discovery provided a solid, natural explanation for at least some of these bursts. A starquake on a magnetar's crust could snap its magnetic field lines, releasing a titanic pulse of radio waves. But the mystery is far from solved because not all fast radio bursts are the same. The real head-scratchers are the repeaters. Most bursts are one-off events, likely caused by a single, catastrophic destruction, like two neutron stars colliding and merging into a black hole. But some sources out in the cosmos fire off multiple bursts over and over again, sometimes in erratic patterns. This completely rules out any theory that requires the source to be destroyed. Whatever is making these repeating bursts survives the event, ready to fire again. So what cosmic engine can produce such unimaginable power repeatedly? The magnetar model still works, as these stars can have multiple quakes, but some scientists have proposed even more exotic origins, like the violent interactions around a supermassive black hole or the collapse of strange, super-dense cosmic strings left over from the Big Bang. And then, of course, there is the speculative but irresistible question. Could some of these signals, especially the complex repeating ones, be artificial? Could they be the leakage from unimaginably powerful alien technology, like propulsion beams for light-sail spacecraft, or simply a cosmic lighthouse built by a civilization saying, "We are here"? While most astronomers strongly favor natural explanations, the sheer extremity of fast radio bursts forces us to consider every possibility. They are cosmic telegrams stamped with a return address billions of light years away, but written in a code we are only beginning to crack. Each flash is a reminder that the universe is not just vast and quiet, but also capable of sudden, brilliant violence. And as our listening posts get more sensitive, the chorus of these strange screams is only growing louder, each one a new piece of a puzzle we do not yet have the picture for. Something is pulling us through the cosmos at over 2 million kilometers per hour. Our entire galaxy, along with every neighboring galaxy in our local group, is caught in a relentless river of motion, all flowing toward a single, invisible point in the distant darkness. This is the mystery of the Great Attractor, a gravitational anomaly so powerful it bends the paths of galaxies, and it lies in a part of the sky we can barely see. For decades, this cosmic tug-of-war presented a profound navigational puzzle. Astronomers mapping the large-scale motion of galaxies in the 1970s and 80s noticed something strange. While the overall expansion of the universe carries galaxies apart, our local region shows a clear additional velocity, a deviation from the smooth Hubble flow. Think of it like floating down a wide, slow river, but suddenly feeling a strong current pulling you sideways toward a hidden waterfall. Every galaxy for hundreds of millions of light years around us is being drawn in the same direction toward the constellation Centaurus. But when we look there with optical telescopes, we see not much. The problem is our own galaxy's dusty, star-filled disk. This band of the Milky Way, which appears as a beautiful milky river in our night sky, acts as a cosmic curtain. It's called the zone of avoidance. Thick clouds of gas and dust, along with the sheer density of stars, block our optical view of the universe beyond in that direction. It's like trying to see a distant city through a dense, brilliant fog. The Great Attractor was literally hiding in our blind spot. To peer through this galactic veil, astronomers had to use different eyes. They turned to telescopes that see in X-ray and infrared light. X-rays punch through dust, revealing the hot gas that permeates giant clusters of galaxies. Infrared light, with its longer wavelengths, can also slip between dust grains, showing the glow of stars otherwise hidden. What these observations revealed was not a single, monstrous object, but an immense concentration of mass, a sprawling supercluster of galaxies. This region, now called the Norma Cluster, is indeed one of the most massive structures in our nearby universe. So, mystery solved, not quite. While the mass of this supercluster is enormous, calculations suggest it might not be quite heavy enough to account for the full strength of the pull we feel. The gravitational current seems too strong for the visible source. This leads to a fascinating possibility. What if the Great Attractor itself is being pulled? Our motion may not be toward a single destination, but part of a much larger, grander flow. Beyond the Norma Cluster lies an even more immense structure, a staggering assembly of galaxy clusters known as the Shapley supercluster, one of the largest concentrations of matter in the observable universe. It is possible that the Shapley supercluster is the ultimate source of the pull, with the Great Attractor merely being a massive waypoint on our journey. We are caught in a cosmic chain of gravity where clusters pull clusters in an endless hierarchy. This changes the picture entirely. We are not just being pulled toward a hidden attractor, we are part of a vast, river-like motion of galaxies on scales almost too large to comprehend, all streaming toward the greatest concentrations of mass in the cosmos. The Great Attractor, then, is less a final answer and more a signpost pointing toward the true giants lurking in the darkness. It reminds us that our place in the universe is not static, but dynamic, a single leaf caught in a gravitational current that spans hundreds of millions of light years. And if such colossal, hidden structures can warp the motion of our entire galaxy, what else lies beyond our current view, silently shaping the fate of everything we know? Sometimes the biggest mysteries are born from the smallest discrepancies. As the Pioneer 10 and Pioneer 11 spacecraft journeyed beyond the orbits of the outer planets, becoming humanity's first emissaries to the interstellar void, scientists tracking their precise trajectories noticed something was off. The probes were slowing down just a tiny bit more than they should have been. This minuscule deviation, a deceleration smaller than a nanometer per second squared, became one of the most tantalizing puzzles in modern space exploration, known simply as the Pioneer anomaly. For over a decade, this faint, persistent tug backward haunted physicists. Every known force was accounted for: the gravitational pull of the sun and planets, the gentle pressure of sunlight itself, even the minuscule drag from the thin dust of the solar system. The math was exhaustive, but the numbers never quite added up. the pioneers were experiencing an extra, unexplained deceleration toward the Sun, as if space itself held a whisper of extra friction. When a measurement contradicts our most trusted models, especially by such a tiny amount, it forces a profound question. Is it an error or a crack in the foundation of physics? The Pioneer anomaly opened that crack just wide enough for wild speculation to pour through. Some researchers proposed it was evidence for dark matter's gravity exerting a subtle pull within our solar system. Others wondered if it pointed to a flaw in Einstein's theory of general relativity itself, suggesting modifications to the laws of gravity on very large scales, an idea known as modified Newtonian dynamics. The most exotic theories even suggested it could be an effect of the universe's expansion acting on the spacecraft locally. The possibility that we were seeing the first hint of new physics from our own backyard was electrifying. But science has a powerful tool for solving such enigmas: patience and relentless scrutiny. The breakthrough came not from a new telescope, but from old data and new computer models. A team of scientists led by Slava Turyshev dove into decades of telemetry, recovering archived data that included not just trajectory information, but the detailed thermal and electrical histories of the spacecraft. They built a stunningly precise virtual model of the Pioneer probes, and they discovered the culprit was not in the stars but in the spacecraft's own design. The Pioneers were powered by radioactive thermoelectric generators. These units produced heat which the spacecraft dissipated through radiation. Crucially, the heat was emitted more strongly from the back of the dish-shaped antenna than from the sides. This created an incredibly subtle but constant thermal recoil force, a photon pressure pushing the craft backward toward the Sun. It was like a car with a slightly misaligned exhaust pipe, where the invisible stream of hot gas provides a tiny, continuous thrust in the wrong direction. Once this anisotropic thermal radiation was meticulously calculated and added to the models, the anomaly vanished. The Pioneers were behaving exactly as Newton and Einstein predicted. So, was it a letdown? Far from it. The resolution of the Pioneer anomaly is a triumph of scientific rigor. It shows that even an effect 10 billion times weaker than Earth's gravity can be detected, measured, and ultimately explained. It underscores that our deepest voyages of discovery are also exercises in extreme precision, where understanding the heat from a light bulb on a spacecraft billions of miles away is as important as mapping distant galaxies. The mystery served as a decades-long masterclass in humility and diligence, reminding us that before we can rewrite the laws of the cosmos, we must first fully understand our own machinery. And it leaves us with a provocative thought. If such a subtle, human-made effect could mimic the signature of new physics, what other whispers in the data are we still misinterpreting? A single, perfect note rang out from the cosmos, and then it was gone. In the early hours of August 15, 1977, the Big Ear radio telescope at Ohio State University was performing its routine scan of the sky, listening for whispers in the radio static. Suddenly, its recorder printed a sequence of letters and numbers that made researcher Jerry Amon's heart stop. The signal was a narrowband radio burst at exactly 1,420 MHz, a frequency that is naturally quiet because it is protected by international agreement, a channel where earthly broadcasting is forbidden so scientists can listen for the universe. It lasted for a full 72 seconds, rising and falling in intensity exactly as a signal from a fixed point in space should, as Earth rotation brought it into the telescope's focus and then carried it away. The data was so strikingly artificial that Amon, reviewing the printout later, circled the alphanumeric code 6EQUJ5, and in the margin he wrote a single, emphatic word: "Wow." That exclamation gave the signal its immortal name. The WOW signal was everything the search for extraterrestrial intelligence, or SETI, had been hoping for. It was strong, it was clear, and it came from a specific point in the constellation Sagittarius. It fit the predicted profile of an interstellar beacon perfectly. The excitement was immediate and electric. Here, at last, was a candidate that could not be easily dismissed as human interference or a natural cosmic crackle. But science demands repeatability, a second act to confirm the discovery. So astronomers pointed every available telescope back at that spot in Sagittarius. They listened for days, then weeks, then years. They scanned that frequency and thousands around it. The silence that followed was absolute. The note never played again. For decades, the WOW signal stood alone, a tantalizing one-off event, a cosmic shout heard by a single ear. Without a repeat, the mystery only deepened. Was it a fleeting message, a lighthouse beam that swept past us only once, or was it something else entirely? The lack of a repeat performance forced scientists to reconsider natural explanations with renewed intensity. One modern hypothesis pointed to a pair of passing comets, discovered years after the signal, that were in the same region of sky. The idea was that clouds of hydrogen gas boiling off the comets could have emitted a strong, narrowband radio signal as they interacted with the solar wind. It was a clever idea, but when researchers recreated the observation with detailed calculations, the numbers did not match up. The comets were not in precisely the right position, and the hydrogen signature they would produce looked different from what was recorded. The comet explanation, while intriguing, left many astronomers unconvinced. Other natural causes, like a bizarre stellar flare or an unknown form of interstellar scintillation, have been proposed, but each comes with its own set of problems. None have been conclusively proven. So the WOW signal remains in a unique category, the strongest, clearest candidate in SETI history that we cannot explain away. It is a ghost in the machine of the cosmos, a 72-second argument that we might not be alone, followed by a 40-year silence that argues we might be. It teaches us a profound lesson about the universe, that it is capable of producing signals indistinguishable from intelligence, and about ourselves, that we must have the patience to wait for a song to play a second time before we can be sure of the singer. That one brief shout from the dark continues to echo, a question mark written in radio waves asking us what we are truly hoping to hear. Beyond the orbit of Neptune, our solar system does not simply fade into an empty void. It is surrounded by a vast, donut-shaped swarm of icy worlds known as the Kuiper Belt, a frozen archive of the solar system's earliest days. This distant realm is home to dwarf planets like Pluto and Eris, and countless smaller chunks of primordial ice and rock. But when astronomers began to map this population in detail, they encountered something deeply puzzling. The number of objects does not gradually thin out as you go farther from the Sun. Instead, it falls off a cliff, around 50 astronomical units from the Sun, which is 50 times the Earth-Sun distance. The population of Kuiper Belt objects plummets almost to zero. It is as if the builders of the solar system simply stopped working at a specific invisible boundary. This sudden edge, known as the Kuiper Belt Cliff, is a mystery written in ice. Our standard models of how the solar system formed predict a gentle decline. The primordial disk of gas and dust that swirled around our infant sun should have distributed material smoothly, with more stuff closer in and less stuff farther out. You would expect to find fewer objects at 50 astronomical units than at 40, and fewer still at 60, but you would not expect to find almost nothing. The cliff suggests something dramatic happened here, a cosmic event that either cleared out the outer reaches or never allowed them to fill up in the first place. One leading theory points to the gravitational hand of an unseen giant. For years, astronomers have tracked the peculiar, clustered orbits of some extremely distant Kuiper Belt objects. Their paths are tilted and grouped in a way that suggests the gentle but persistent tug of a massive perturber, a hypothetical world several times the mass of Earth orbiting far beyond Pluto. This is the proposed planet 9. If it exists, its gravity could have sculpted the outer solar system over billions of years, perhaps shepherding many of the objects that should be beyond the cliff into different, harder-to-find orbits, or even ejecting them from the solar system entirely. The cliff in this scenario is the edge of Planet Nine's grazing ground, but there is another, more ancient possibility. Perhaps the cliff is a fossil, a preserved edge of the very disk from which our planets were born. The solar nebula might not have been a perfectly smooth, infinite cloud. It could have had a sharp outer boundary, like a pancake with a crisp edge, perhaps truncated by a passing star in the Sun's birth cluster long ago. In that case, the Kuiper Belt Cliff marks the literal edge of the construction zone. Nothing exists beyond it because there was never any raw material out there to begin with. Each theory paints a different picture of our cosmic neighborhood. One is dynamic, involving a hidden planet still shaping the solar system today. The other is static, a frozen snapshot of a fleeting moment 4.5 billion years in the past. Finding the answer requires peering deeper into that darkness, searching for the faint, slow-moving dots that could map the gravity of a hidden world or confirm the absence of one. This invisible line in space is more than a curiosity, it is a boundary question. It asks us what defines the true edge of our sun's influence and how violent or quiet the nursery of our planet truly was. The answer lies in the slow dance of ice in the deep freeze, a dance we are only just beginning to see. The universe's oldest light holds a secret that makes cosmologists deeply uncomfortable. This is the cosmic microwave background, the faint, cold glow that fills every corner of space, the cooled and stretched remnant of the universe's fiery birth nearly 14 billion years ago. It is our most pristine snapshot of the infant cosmos, a map of tiny temperature differences, mere millionths of a degree, that reveal the seeds from which all galaxies grew. According to our foundational theories, this background should be the very picture of cosmic democracy. The universe should have no center, no edge, and no preferred direction. This cosmological principle states that on the largest scales, the universe looks roughly the same everywhere and in every direction. The CMB should be isotropic, a perfectly random and even distribution of hot and cold spots, like the static on an old television tuned to a dead channel. But when scientists created exquisitely detailed maps of this radiation, first from the WMAP satellite and then from Planck, they saw something that should not be there. A strange, large-scale pattern emerged, an alignment that has been grimly nicknamed the axis of evil. The hot and cold spots in the CMB are not completely random. They show a curious correlation, a subtle preference that aligns with the plane of our own solar system. It is as if the universe's birth cry somehow knew about the flat disk in which Earth orbits the Sun, billions of years before that disk even existed. This alignment defies the cosmological principle at its core. Why would the grand structure of the entire universe care about our tiny, local neighborhood? The implications are unsettling. One possibility is that it is a colossal statistical fluke. When you analyze a vast amount of data, you can sometimes find patterns that look significant purely by chance. Scientists have run countless simulations of a random, isotropic universe, and yes, sometimes these simulations produce apparent alignments. But the axis of evil is a particularly stubborn and large-scale fluke that has persisted through multiple space missions and increasingly precise data. It refuses to be washed away by better measurements. Another, more pragmatic explanation is that it is an artifact, a contamination from our own cosmic backyard. Perhaps something within our solar system or our Milky Way galaxy is imprinting this signal onto the CMB data. Dust, magnetic fields, or even the motion of our solar system through space could, in theory, create a false pattern. Teams have worked tirelessly to subtract every conceivable local foreground signal, but the alignment persists, haunting the cleaned maps. If it is not a fluke and not an artifact, then we are left with the most profound and disturbing possibility. The axis of evil could be a real feature of the cosmos, a crack in the foundation of modern cosmology. It would suggest that the universe does have a preferred direction, a large-scale structure or anisotropy that makes one axis different from others. This could mean our location is special in some way, reviving a kind of modern cosmic centeredness that science has worked for centuries to dispel. It might even hint that the universe is not infinite and uniform, but has a structure on scales larger than we can observe, like a vast crystal with a grain to it. The name Axis of Evil, coined half in jest, reflects just how philosophically troubling this finding is to the Standard Model. It points toward a universe that is not as simple nor as random as we have assumed. Whether it is a flaw in our data, a flaw in our statistics, or a flaw in our fundamental understanding, this eerie alignment in the ancient light is a mystery we cannot ignore. It asks us if we are seeing a ghost in the machine of creation, or if the machine itself is far stranger than we ever dreamed. Our cosmic recipe has a stubborn, persistent error. The first few minutes after the Big Bang were not just a chaotic explosion, but a precise, universe-scale nuclear reactor. During this fleeting period, known as Big Bang nucleosynthesis, the primordial soup of protons and neutrons fused to form the first atomic nuclei, the building blocks for all the stars and planets to come. The calculations for this process are a triumph of modern cosmology. They predict with stunning accuracy how much of the universe should be hydrogen, about 75% by mass, and helium, about 25%. The observations match perfectly, but there is a third tiny ingredient on that primordial list, lithium-7, and here the math and the universe violently disagree. The theory says old stars, the ancient fossils of the cosmos, should contain about 3 times more lithium than we actually see. This is the lithium problem, a small number with enormous implications, a crack in our otherwise flawless story of creation. To understand why this is so troubling, picture the early universe as a rapidly cooling pot. For the first few minutes, it was hot and dense enough for nuclear fusion to occur everywhere at once. Protons and neutrons collided, forming deuterium, then helium, and a trace amount of lithium-7, the stable isotope with 3 protons. As the universe expanded and cooled, the pot thinned out, and this cosmic cooking stopped, freezing in the abundances of these light elements. This process is not a vague guess. It is a precise set of equations tied directly to the density of the universe and the number of types of neutrinos. The fact that the hydrogen and helium predictions are spot on proves our model for the universe's first 3 minutes is overwhelmingly correct. That makes the lithium discrepancy not a minor detail, but a glaring anomaly, like perfectly predicting every ingredient in a cake except for the sugar, which is mysteriously only 1/3 of what the recipe calls for. So where did the lithium go? If it was forged in the Big Bang, it should be present in the oldest stars, which formed from that pristine, uncontaminated gas. Yet when astronomers measure these ancient suns, the lithium is consistently missing. One leading idea is that the lithium was destroyed later. Perhaps these old stars, over their billions of years of life, have internal processes that slowly drag surface lithium down into their hotter interiors, where it is fused into other elements. This is plausible, but modeling stellar interiors is incredibly complex, and it is not clear if this process could account for the full factor of 3 shortfall across all the stars we observe. It would mean our understanding of how stars churn and mix their material is fundamentally incomplete. More radical solutions point back to the beginning itself. Could our understanding of nuclear physics in those first few minutes be wrong? Perhaps unknown particles, like certain types of dark matter, were present and altered the nuclear reaction rates. Or maybe the lithium was destroyed shortly after its creation by hypothetical, energetic particles that have long since faded from the cosmos. There is even the exotic possibility that some of the primordial lithium settled into the cores of ancient stars we can no longer see, hiding it from our telescopes. Each potential fix, however, risks upsetting the perfect balance that so accurately gave us the hydrogen and helium we see. It is a delicate puzzle. Change one piece to fit the lithium, and you risk breaking everything else that works. This tiny deficit is a masterclass in scientific humility. It reminds us that even our most successful stories are still being written. The universe followed its recipe almost perfectly, but left behind one inconsistent measurement, a clue that something in our kitchen, either during the first cook or in the storage afterward, is not quite what we think. Solving the lithium problem might not require a revolution in cosmology, but it will demand a deeper, more subtle understanding of the nuclear furnaces of the first stars or the ghostly physics of the first moments. It is a whisper from the dawn of time, telling us that a small piece of the story is still missing. The most fundamental laws of physics are at war inside the darkest objects in the universe. This is the black hole information paradox, a conflict so deep it questions our understanding of reality itself. The problem begins with a simple principle from quantum mechanics, the idea that information cannot be destroyed. Information, in this sense, is the complete set of quantum details that describe every particle, every atom, everything that makes you, you, or a star, a star. If you burn a book, the information in its pages is not truly lost. It is just chaotically transformed into smoke and heat. In principle, a being with perfect knowledge could reverse the process, gathering every ash particle and photon, and reconstruct the original book. This principle of information conservation is a bedrock of our quantum world. Then along came Stephen Hawking. In the 1970s, he made a shocking theoretical prediction. Black holes, those gravitational prisons from which not even light can escape, are not completely black. Using the strange rules of quantum mechanics near the event horizon, Hawking showed that black holes should slowly leak radiation, now called Hawking radiation. This radiation is not made from the stuff inside the black hole. It is created from the violent energy of the gravitational field right at the edge. Over unimaginable eons, this slow leak causes the black hole to lose mass and eventually evaporate completely, vanishing in a final, faint puff of radiation. And here lies the catastrophic paradox, that Hawking radiation is random. It carries no specific information about what fell into the black hole. It is pure thermal noise, like the static from an old radio. So, if the black hole evaporates away, leaving behind only this generic heat, what happened to the information of all the stars, planets, or books that ever fell in? According to Hawking's original math, the information is permanently erased from the universe, violating the most sacred rule of quantum physics. For decades, this was the standoff, general relativity saying black holes destroy everything, quantum mechanics saying that is impossible. The conflict hinted that our two greatest theories of reality are fundamentally incompatible, at least under such extreme conditions. To resolve the paradox, physicists have been forced to propose ideas that sound like science fiction. One of the most profound is the holographic principle. This mind-bending concept suggests that all the information that falls into a black hole is not lost inside its volume, but is instead encoded on its two-dimensional surface, the event horizon. Think of it like a cosmic thumb drive, where the three-dimensional reality of the interior is projected from a two-dimensional film of quantum data on the boundary. When the black hole evaporates, this information is slowly and chaotically released back into the universe through subtle correlations in the Hawking radiation. In this view, information is scrambled, not destroyed. Another, more violent solution is the firewall hypothesis. It proposes that the event horizon is not a smooth, empty space as Einstein predicted. Instead, it is a searing wall of high-energy particles, a literal firewall that incinerates anything crossing it. This would protect information from falling in by destroying it at the door, but it blatantly violates the principle of equivalence in general relativity, which states that falling through an event horizon should feel like empty space. You cannot have both a smooth horizon and a firewall, so one theory must break. The black hole information paradox is more than an abstract puzzle. It is a direct probe into the heart of quantum gravity, the still missing theory that must unite the very large with the very small. It forces us to ask what truly happens at the edge of reality. Is spacetime fundamentally smooth, or is it pixelated? Is our three-dimensional world just a holographic projection? The answers, when they come, will not just tell us about black holes, but about the underlying code of the cosmos itself. Our solar system is not quite the orderly, flat disk we often picture. Look at a scale model, and you will find a curious kink in its geometry. The Sun itself, the anchor of our entire planetary family, spins on an axis that is tilted by about 6 degrees compared to the plane in which all the planets orbit. This solar obliquity is a small number with big implications, a silent clue that our system's birth was not perfectly calm. According to the standard story, the solar system formed from a vast, spinning cloud of gas and dust called the solar nebula. As this cloud collapsed under its own gravity, conservation of angular momentum forced it to flatten into a disk like a cosmic pizza crust spinning in the void. The Sun coalesced at the center, and the planets formed from the material in that flat plane. In this elegant model, the Sun's spin axis should be perfectly perpendicular to the planetary plane. But it is not. That 6-degree tilt tells us something knocked the system askew, either during its infancy or sometime later. One of the most compelling theories reaches back to the Sun's earliest days when it was not alone. Stars are born in crowded nurseries surrounded by hundreds or thousands of stellar siblings. In such a dense environment, close encounters are not just possible, they are expected. A passing star venturing too close to our young solar system could have exerted a significant gravitational tug. This tug would not have neatly pushed individual planets, but could have torqued the entire system, tilting the Sun's axis relative to the preserved orbital plane of the planets. Think of it like a gentle but firm hand brushing against a spinning top, nudging its axis of rotation just a bit. This stellar flyby, happening over 4 billion years ago, would have been a fleeting event, but its fingerprint would be frozen into our architecture forever. Another possibility points to a hidden presence still within our system today. The hypothetical planet 9, a massive world thought to orbit far beyond Neptune, could be the culprit. If such a planet exists on a highly tilted orbit itself, its immense gravity, exerted over billions of years, could slowly but surely have pulled on the entire solar system, causing the Sun's axis to gradually wobble into its current misaligned state. This would be a slower, more persistent process than a stellar flyby, a constant gravitational nudge from the outer darkness. To visualize this, picture a classic orrery, a mechanical model of the solar system with all the planets orbiting in a neat flat plane. Now imagine carefully tilting the central light bulb representing the Sun, while leaving all the orbiting planets in their original plane. That is the skew we see. It is a subtle effect, but for scientists who expect cosmic mechanics to follow clean, predictable rules, it is a glaring anomaly. Solving this mystery is not just about fixing a tilted Sun. It is about forensic astronomy, piecing together the violent or dynamic history of our own cosmic neighborhood. Did a rogue star brush past us, leaving a permanent scar on our geometry? Or is the gravitational hand of an unseen giant still actively shaping our system from the shadows? That 6-degree tilt is a question mark written in the alignment of our star, asking us to reconsider how quiet and isolated our birthplace truly was. The orderly tilt of our Sun is a clue to ancient chaos, but sometimes the chaos arrives from beyond our doorstep. In October 2017, astronomers at the Pan-STARRS telescope in Hawaii spotted a faint point of light moving at breathtaking speed. Its trajectory was unlike anything seen before, a hyperbolic path so extreme it could only mean one thing: this visitor was not from our solar system. It was the first confirmed interstellar object ever observed, and it was given a name that means scout from the distant past in Hawaiian, Oumuamua. From the moment it was detected, Oumuamua was an anomaly. It had already made its closest pass to the sun and was speeding away, a fleeting guest already saying goodbye. Astronomers had only weeks to scramble every telescope on Earth and in space to study it before it faded into the darkness forever. What they learned in that frantic window was deeply puzzling. First, its shape. By measuring how its brightness changed dramatically as it tumbled, scientists deduced it was highly elongated, perhaps 10 times as long as it was wide. Imagine a cosmic cigar or a flattened pancake tumbling chaotically through space. This was nothing like the typical roundish asteroids or comets from our own solar system. Second, it showed no visible coma, the fuzzy cloud of gas and dust that surrounds a comet when the sun's heat vaporizes its ice. As Oumuamua swung around the sun, it should have erupted with jets of gas if it were a typical icy body. Our telescope saw nothing, yet in the most baffling twist, precise tracking revealed it was not moving solely under the influence of the sun's gravity. It was experiencing a tiny but clear non-gravitational acceleration, as if an unseen, gentle force was giving it an extra push. For comets, this is common, caused by jetting material acting like a rocket engine. But Oumuamua showed no jets, no dust, no visible evidence of what was pushing it. The scientific community scrambled for natural explanations. The leading theory today paints a dramatic picture. Oumuamua could be a shard of nitrogen ice, a peculiar fragment from a distant Pluto-like world in another star system. A violent collision or gravitational encounter could have ripped a chunk from that dwarf planet's surface and hurled it into interstellar space. As it approached our sun, the intense heat would have vaporized the nitrogen ice from its surface, providing the invisible thrust that accelerated it without producing a visible dusty coma. This theory elegantly explains the acceleration and the lack of a tail, framing Oumuamua as a strange but natural interstellar iceberg. But the object's extreme shape and its mysterious behavior also open the door to more speculative ideas. Harvard astronomer Avi Loeb famously proposed that we must consider an artificial origin. Could Oumuamua's flat, pancake-like geometry and its light-induced acceleration be the hallmarks of a discarded light sail? A solar sail is a proposed spacecraft propulsion method that uses the gentle pressure of sunlight for thrust, requiring no fuel. Loeb suggested Oumuamua could be a piece of such technology, a derelict probe or a fragment of an alien vessel that had long ago served its purpose. While most astronomers strongly favor the nitrogen iceberg hypothesis, Loeb's argument highlights a crucial point. When we encounter something truly unprecedented, we must rigorously rule out all possibilities, even the extraordinary ones. Oumuamua is now gone, a silent speck racing toward the constellation Pegasus, never to return. Its brief visit left behind a profound legacy. It proved that interstellar objects are passing through our solar system all the time, a fact confirmed just 2 years later by the clearly cometary interstellar visitor Borisov. But Oumuamua remains unique, the first and the strangest. It was a cosmic postcard from a place we will never know, written in a language of shape, motion, and light that we are still struggling to translate. Whether a shard of an alien Pluto or a piece of forgotten technology, its true nature is a mystery sealed in the vault of deep space, a reminder that sometimes the most important discoveries are the ones that get away. The center of our galaxy should be a predictable, if violent, place. We know of the supermassive black hole, Sagittarius, a star, and the dense clusters of ancient stars swirling around it. We expect a certain background hum of gamma rays, the highest energy light, from known sources like spinning neutron stars and cosmic rays slamming into gas clouds. But when scientists analyzed years of data from the Fermi Gamma Ray Space Telescope, they found something that did not fit. The galactic center is glowing with far more gamma radiation than it should. This mysterious surplus, dubbed the galactic center excess, is a bright, unexplained fog at the heart of the Milky Way, and it might be our first direct glimpse of the universe's most elusive substance. Picture a map of gamma-ray light. The center of our galaxy shines brilliantly as anticipated, but when researchers carefully subtracted the light from every known and modeled source, the pulsars, the cosmic ray collisions, all of it, a persistent spherical glow remained. It is not a point source, but a diffuse, symmetrical halo of excess energy centered precisely on the galactic core. This is not noise or a statistical fluke, it is a real signal screaming for an explanation. Two compelling and radically different theories have emerged to explain this strange glow, and they represent a fundamental fork in the road for modern physics. The first explanation is astrophysical, complex, but entirely within the realm of known objects. The center of the galaxy is a crowded metropolis of ancient stars. Among them, theorists suggest, could be a vast, unseen population of millisecond pulsars. These are neutron stars that have been spun up to incredible speeds by siphoning material from a companion star, whirling hundreds of times per second. Each one would be a faint, point-like source of gamma rays. Individually, they are too dim for Fermi to resolve at that distance, but collectively, thousands or even millions of them could blend together to create the exact diffuse glow we see. It would be like looking at a distant city at night, your eyes unable to pick out individual streetlights, but seeing their combined light as a general haze on the horizon. This is a perfectly reasonable solution, requiring no new physics, just a lot of very old, very fast stars we have not spotted yet. The second explanation is the one that sends a thrill through the world of particle physics. This glow could be the long-sought signature of dark matter annihilation. Here is how it might work. According to some leading theories, dark matter particles are their own antimatter counterparts. When two of them collide, they can annihilate each other in a flash of pure energy, producing a cascade of particles that ultimately include gamma rays. And where would such collisions be most frequent? In the very places where dark matter is densest. The center of our galaxy is thought to be the peak of a vast, invisible dark matter halo. If these particles are annihilating anywhere, they would be doing it there most brightly. The spherical shape of the excess glow matches predictions for a dark matter halo's density profile far better than it matches the more clumpy distribution of stars. In this scenario, we are not looking at stars at all, but at the faint, fading embers of invisible particles destroying each other in the dark. This is why the galactic center excess is such a gripping mystery. It sits at a perfect crossroads. One path leads us deeper into the complex astrophysics of stellar graveyards. The other path leads us to the edge of a revolution, offering the first direct, tangible evidence for the particles that make up 27% of the cosmos. The next steps involve sharper eyes and cleverer analysis. New telescopes like the upcoming Cherenkov telescope array will try to resolve the glow into individual points, hunting for those hidden pulsars. If they find them, the case for dark matter weakens, but if the glow remains stubbornly smooth and diffuse, the dark matter hypothesis grows stronger. We are left watching the heart of our own galaxy, waiting to see if its strange light is the glow of forgotten stars or the funeral pyre of the universe's greatest ghost. Two of our most trusted cosmic measuring tapes disagree, and the discrepancy is tearing a hole in our standard model of the universe. This is the Hubble tension, a crisis in cosmology that grows more severe with every new, precise measurement. At its heart is a single, fundamental number, the Hubble constant, which tells us how fast the universe is expanding today. We have two brilliant, independent ways to measure it, and they keep giving us stubbornly different answers. It is as if two identical clocks, built by master craftsmen and checked 1,000 times, are ticking at irreconcilably different speeds. The first method builds a cosmic distance ladder, one careful rung at a time, using objects within our relatively local universe. Astronomers start with Cepheid variable stars, whose predictable pulsations allow us to measure their true brightness and thus their distance. They use these to calibrate the next rung, Type 1, a supernova, those brilliant standard candles that can be seen in faraway galaxies. By measuring how fast these galaxies are moving away from us and knowing precisely how far away they are, scientists can calculate the expansion rate right now. This local ladder method, refined over decades, gives us a consistently high value for the Hubble constant. The second method takes a completely different approach, looking back to the infant universe. It uses the detailed map of the cosmic microwave background, that frozen echo of the Big Bang. By analyzing the subtle patterns in this ancient light, scientists can deduce the ingredients of the early cosmos, its density, and how fast it was expanding back then. Using our well-tested model of cosmic evolution, they can run the clock forward to predict what the expansion rate should be today. This early universe method from the Planck satellite data gives us a consistently lower value. The numbers themselves are incredibly precise, but they do not overlap. The difference is only about 10%, but in the world of precision cosmology, that gap is a yawning chasm. It is far larger than the estimated margins of error for either technique. This is not a small rounding issue, it is a direct contradiction. One of our most fundamental observations about the present universe does not match the story written in its oldest light. So what could be causing this tension? The first possibility is the most humble, a systematic error. Perhaps there is a subtle flaw we have not yet found in how we measure the distances to Cepheid stars or the brightness of supernova. Teams are obsessively checking and rechecking, using new tools like the James Webb Space Telescope to remove any uncertainty. Yet, as the measurements get sharper, the discrepancy persists, even grows. This points to the far more exciting possibility, new physics. If the measurements are both correct, then our standard model of cosmology is missing a key ingredient. Something must have changed the expansion history of the universe between the early afterglow and the present day. Cosmologists are scrambling to propose what that could be. Perhaps dark energy, the force driving the acceleration, is not a constant but an evolving entity that grew stronger more recently. Maybe there is a new type of neutrino, a ghostly particle that speeds through the cosmos, altering the energy balance at a crucial moment. Other ideas involve primordial magnetic fields or even slight interactions between dark matter and dark energy. Getting the right number is not just an academic exercise, it is crucial for understanding the ultimate fate of everything. The Hubble constant sets the age, size, and future trajectory of the cosmos. A faster expansion rate suggests a younger, more dynamic universe with a different destiny than a slower one. This tension is a gift, a clear signal that our map of reality is incomplete. It forces us to question our assumptions and search for the missing piece that will make the early universe and the present day tell the same story. The disagreement between two clocks means one of them, or perhaps the flow of time itself, is not what we thought. Mars holds its breath, and we are straining to hear the whisper. For over a decade, our robotic explorers on the Red Planet have been sniffing the thin, cold air, and they have caught a scent that should not be there: methane. This simple gas, a single carbon atom bound to 4 hydrogens, is at the center of one of the most tantalizing mysteries in our solar system. On Earth, methane is a signature of life. Vast amounts are burped by cows, released by decaying plants in wetlands, and crucially, produced by vast colonies of microbes called methanogens that thrive in places without oxygen, like deep underground or in the guts of animals. Of course, methane can also be made without any biology at all, through geological processes like serpentinization, where certain rocks react with water and produce the gas as a byproduct. But finding it on Mars, especially in the pattern we see, sends a jolt of excitement through every scientist searching for life beyond Earth. The puzzle began in earnest with the Curiosity rover. After landing in Gale Crater in 2012, its onboard laboratory, the Sample Analysis at Mars Instrument, began taking small sips of the atmosphere. And it found methane not in a constant, steady background, but in sudden, sharp spikes. The gas would appear, raising the concentration to levels 10 times the normal baseline, and then within weeks or even days, it would vanish almost completely. Later, orbital data from the European Space Agency's Mars Express and the ExoMars Trace gas orbiter confirmed these detections, sometimes showing larger regional plumes. This intermittent nature is the second and perhaps even more baffling part of the mystery. If methane is being released from somewhere on Mars, what is destroying it so quickly? In Earth's atmosphere, methane can persist for years, slowly broken down by chemical reactions. But the Martian air is thin and lacks the complex chemistry that would normally scrub methane away so rapidly. Some unknown, highly efficient destructive process must be at work on the red planet, a process we do not yet understand. So where is the methane coming from? The possibilities split into two profound narratives. The first is the geological story. Mars is geologically active in subtle ways. There is evidence of ancient volcanism, and the subsurface could still hold pockets of warmth. The process of serpentinization could be occurring where underground water meets specific types of rock, like olivine, slowly seeping methane into the atmosphere. The seasonal changes could be explained by temperature shifts, where the Martian soil acts like a sponge, trapping the gas when cold and releasing it when warmer. This is a perfectly valid, lifeless explanation, but the other narrative is the biological one. Imagine a scenario where, deep beneath the frozen, radiation-blasted surface of Mars, in a protected aquifer or a briny pocket of liquid water, ancient microbial life clings to existence. These hypothetical Martian microbes, like their earthly counterparts, could be metabolizing hydrogen and carbon dioxide, producing methane as a waste product. A small shift in the subsurface, a crack from a marsquark or a seasonal thaw, could release a puff of their gaseous exhaust into the atmosphere above. That is the breathtaking possibility. We are not looking for little green men, but for the faint chemical signature of a buried, microscopic biosphere. This is why the Martian methane mystery is so critical. It transforms Mars from a dusty, dead world into a planet with an active chemical cycle, one that we have not fully mapped. Every new detection, every conflicting measurement between rover and orbiter adds a piece to a puzzle we cannot yet see. Is it the faint, lingering breath of a hidden ecosystem, or just the slow geological sigh of a cooling planet? The answer lies not in the air itself, but in the hidden sources below. Future missions equipped to drill deeper or to measure the isotopes in the methane, which can act as a fingerprint of its origin, will be our guide. For now, the red planet keeps its secret, offering us whiffs of a promise, a ghost in the thin, cold air that refuses to be explained away. A star is blinking, and we do not know why. Among the hundreds of thousands of suns monitored by the Kepler Space Telescope, one stood out not for its brilliance but for its bizarre, erratic dimming. Catalogued as KIC 8462852, it became famous as Tabby's star, named for astronomer Tabitha Boyajian, who led its investigation. Its light curve, the steady graph of its brightness, looked like nothing ever seen before. Instead of the clean, periodic dips caused by an orbiting planet, Tabby's star showed sudden, dramatic plunges. Its light would drop by staggering amounts, up to 22%, in chaotic, asymmetrical patterns. These were not the gentle 1% shadows cast by a Jupiter-sized world. These were colossal, irregular eclipses, as if something vast and shapeless were drifting in front of the star. The discovery itself was a triumph of human curiosity, made possible by the Planet Hunters project, where citizen scientists sifted through Kepler's public data, their pattern-recognizing eyes catching what automated algorithms might have missed. They flagged this star as deeply weird, and the professional astronomers took notice. The immediate task was to rule out the obvious. Could it be a swarm of planets? No, the dips were far too deep and irregular. A young star still surrounded by a clumpy, forming planet disk. The star was mature, showing no other signs of youth. One of the first natural explanations proposed was a giant family of comets. Imagine a vast cloud of icy fragments, perhaps stirred up by the gravity of a passing star, now orbiting in a dense, ragged swarm. As these comet nuclei and their long, dusty tails passed in front of Tabby's star, they could block its light in those strange, deep, and irregular ways. It was a plausible, if extraordinary, scenario requiring thousands of giant comets on orbits that would inevitably decay. Another idea pointed to the aftermath of a cosmic catastrophe, the dusty debris from a titanic planetary collision, like the one that formed our own moon but on a far grander scale. A cloud of pulverized rock and vaporized material could create a complex, evolving shadow. Yet, as observations continued, an even stranger long-term trend emerged. Historical data from old photographic plates suggested Tabby's star had also been gradually fading over the past century. This compounded the mystery, suggesting both sudden, sharp eclipses and a slow, persistent dimming were at work. The combination of bizarre short-term behavior and a century-long fade was so peculiar it sparked the most famous speculative theory of all, the alien megastructure. Could the dips be caused by a partially constructed Dyson swarm? This hypothetical technology, proposed by physicist Freeman Dyson, involves a civilization capturing a star's energy by surrounding it with a vast array of solar-collecting satellites or habitats. A partially built, lopsided swarm could indeed cause irregular, deep dimmings. The idea captured the public imagination, a tantalizing thought that we might be witnessing the signature of a civilization so advanced it was restructuring its sun. Science, however, demands evidence over excitement. Follow-up observations across the electromagnetic spectrum provided the crucial clues. When Tabby's star dimmed in visible light, it dimmed less in infrared light. This is a critical fingerprint. Large, solid structures like megastructures or planets would block all wavelengths equally. But dust, composed of tiny particles, scatters and absorbs blue light more than red, causing exactly the wavelength-dependent dimming that was observed. The data pointed overwhelmingly to dust. The current favored explanation is a circumstellar dust cloud, possibly from the breakup of a moon or a swarm of asteroid-like bodies, creating a complex, evolving ring of fine debris that occasionally clumps together. The long-term dimming could be from a larger, more diffuse cloud of dust on a wide orbit, slowly drifting into our line of sight. So, while the alien megastructure hypothesis opened our minds to extraordinary possibilities, the mundane signature of dust seems to be the answer. Yet, in a way, the mystery deepens. What event creates such an immense, complex, and long-lived dust cloud around a normal star? Tabby's star remains a unique laboratory, teaching us that nature's repertoire of cosmic oddities is far richer than we imagined, capable of producing signals so strange they briefly let us dream of builders among the stars. Our two most successful theories of reality cannot both be true. Einstein's general relativity paints a breathtaking picture of the cosmos, where spacetime is a smooth, continuous fabric, warped and curved by mass and energy like a trampoline under a heavy weight. This elegant geometry dictates the motion of planets, the bending of light, and the very expansion of the universe. It works perfectly on the grand stage. But in the microscopic realm, quantum mechanics reveals a universe of chaos and chance, where particles flicker in and out of existence and nothing is certain until it is measured. These two pillars of modern physics are incompatible, and their collision point is the very fabric of existence itself. This is the ultimate mystery, the quantum nature of spacetime. To understand the problem, think of a calm, glassy pond. From a distance, its surface appears perfectly smooth and continuous. This is the spacetime of general relativity, a seamless stage on which the drama of the cosmos plays out. But if you could shrink down to the scale of individual water molecules, that smooth surface vanishes. You would see a chaotic, frothing frenzy of molecules jostling and colliding. Quantum mechanics insists that spacetime, at its unimaginably small heart, must be like this, a seething quantum foam. The scale at which this frothiness should dominate is called the Planck length, a distance so tiny that a single proton is larger by a factor of 10 trillion trillion. At this scale, the smooth fabric of relativity should dissolve into a probabilistic storm of virtual particles and wormholes popping in and out of existence. The conflict is absolute. Relativity needs a smooth, deterministic stage. Quantum mechanics insists the stage itself is made of unpredictable, jittery actors. This is not just a philosophical disagreement. It means our physics breaks down at the centers of black holes and at the very first moment of the Big Bang, where density and energy become infinite. To resolve this, we need a theory of quantum gravity, a single framework that describes the rules for the universe's underlying structure. Two of the most prominent contenders offer wildly different visions of this quantum reality. String theory proposes that the fundamental ingredients of the universe are not point-like particles, but unimaginably tiny, vibrating strings. Each different vibration mode corresponds to a different particle, like a guitar string playing different notes. In this view, spacetime itself emerges from the collective behavior of these strings. It is a symphony where the smooth fabric we experience is the harmonious average of countless vibrating threads. String theory requires extra dimensions of space, curled up so small we never perceive them, and it suggests a multiverse of possible cosmic configurations. Loop quantum gravity takes a more direct approach. It suggests that spacetime is not continuous, but is actually woven from finite, discrete loops, a fabric of interwoven threads of space. Picture a knitted sweater. From afar, it looks like a continuous material, but up close you see it is made of individual, connected loops. In this theory, there is a smallest possible unit of space, a quantum of volume, and a smallest tick of time. You cannot divide space or time further than this, which banishes the infinities that plague our current models. Here, the Big Bang might not have been a singularity, but a big bounce from a previous collapsing universe. Both theories are mathematically beautiful and incredibly complex, but they make predictions that are, for now, agonizingly difficult to test. They are like maps of a continent we cannot yet sail to. Yet the quest to solve this mystery is the most fundamental in all of science. It asks what the universe is made of at its core. Is it a cosmic symphony of strings or a tapestry of woven loops? The answer will rewrite our origin story, tell us what truly happens inside a black hole, and reveal whether time itself is fundamental or merely an illusion emerging from a deeper quantum reality. We are searching for the grammar of existence, the rules that wrote the first page of everything. The universe is firing bullets at us, and we have no idea who is pulling the trigger. From the depths of space, atomic nuclei, often just single protons, are screaming toward Earth, carrying energies that defy comprehension. These are ultra-high energy cosmic rays, and they pack a punch millions of times more powerful than anything the Large Hadron Collider can produce. A single one of these subatomic particles hits our atmosphere with the kinetic energy of a professionally thrown baseball, all concentrated into a speck smaller than an atom. The collision is catastrophic, creating a vast, cascading shower of secondary particles that rains down over many square miles. Detecting these rare events requires an observatory on a continental scale, like the Pierre Auger Array in Argentina, which uses thousands of water tanks and fluorescence telescopes to watch for the faint glow of these particle avalanches sweeping across the sky. The mystery is not their existence but their origin. Where in the cosmos are nature's particle accelerators, and how do they work? The challenge is immense. First, these rays are incredibly rare. At the very highest energies, perhaps only one particle strikes each square kilometer of Earth per century. You need a detector the size of a small country just to catch a handful of events each year. Second, and more frustrating, cosmic rays are not neutral photons traveling in straight lines. They are charged particles, and as they streak across the universe, they are whipped and curved by the tangled magnetic fields that fill interstellar and intergalactic space. By the time one reaches us, its path is a hopelessly scrambled mess. Tracing it back to its source is like trying to find which specific tree a leaf came from after it has been blown through a hurricane. So we must become cosmic detectives, looking for correlations and statistical hints. When the highest energy events are mapped, their arrival directions seem to point vaguely toward areas of the sky with extreme astrophysical phenomena. One prime suspect is the active galactic nucleus, the supermassive black hole at the heart of a galaxy that is actively feeding. As matter spirals into the black hole at nearly light speed, it creates jets of plasma that blast out across millions of light years. These relativistic jets could potentially accelerate protons to the energies we see. Another candidate is the gamma-ray burst, the most violent explosion in the universe since the Big Bang, likely caused by the collapse of a massive star or the merger of neutron stars. The sheer, focused energy of such an event could act as a cosmic cannon, but there is a more exotic possibility lurking in the shadows. What if these particles are not accelerated at all, but are the decay products of something left over from creation? Some theories propose the existence of super-heavy dark matter particles, relics from the early universe with masses trillions of times that of a proton. If one of these monsters were to decay, it could spit out an ultra-high energy proton right in our own galactic neighborhood, explaining how such a fragile particle could have traveled vast distances without being destroyed. Each theory has its problems. Active galactic nuclei and gamma-ray bursts are far away, and the particles would lose energy interacting with the cosmic microwave background over such vast journeys. Local dark matter decay solves the travel problem, but requires a whole new type of particle we have never seen. The puzzle remains a testament to the raw, untamed power lurking in the cosmos. We are being bombarded by the universe's most energetic shrapnel, and we are still searching for the explosion. Our cosmic fate is written in the push and pull between gravity and dark energy. The ultimate destiny of everything we see, from the smallest atom to the largest galaxy cluster, hinges on a simple cosmic balance: the density of matter and energy in the universe. For most of scientific history, we envisioned three classical endings, three starkly different final chapters for the cosmos. The first is the Big Crunch, a dramatic reversal of the Big Bang. If there were enough matter in the universe, gravity would eventually overcome the expansion, pulling all galaxies back together in a cataclysmic collapse. Space itself would contract, temperatures would soar to infinity, and the universe would end in a fiery singularity, a mirror image of its birth. The second is the heat death, also called the Big Freeze. This is the opposite scenario, where the density of matter is too low to ever halt the expansion. The universe would continue expanding forever, its energy spreading thinner and thinner. Stars would exhaust their fuel, galaxies would drift apart into darkness, black holes would evaporate via Hawking radiation, and over trillions upon trillions of years, the cosmos would become a vast, cold, and nearly empty void where even atomic motion slows to a near standstill. The third and most violent is the Big Rip. This scenario requires a specific, phantom form of dark energy whose repulsive force grows stronger over time. In this end, dark energy would not just push galaxies apart, but would eventually overcome every binding force. First galaxy clusters, then galaxies themselves would be torn asunder. In its final moments, this phantom force would rip apart stars, planets, molecules, atoms, and even the fabric of spacetime itself. the universe would end not with a collapse or a fade, but with a catastrophic, instantaneous shredding. So which of these fates awaits us? The current evidence from the accelerating expansion driven by dark energy points overwhelmingly toward a version of the heat death. The universe's density appears too low for a big crunch, and for now, dark energy seems consistent with a constant force, not a phantom one. Our best prognosis is an eternal, cooling expansion. But this is where the mystery deepens, because our prognosis is only as good as our understanding of dark energy, and we fundamentally do not know what it is. If dark energy is not a cosmological constant, but a dynamic field that evolves, the entire story could change. Perhaps the repulsive force will weaken in the distant future, allowing gravity to reassert itself and leading to a delayed big crunch after all. Or perhaps it will strengthen, making the big rip inevitable. There is even the profoundly beautiful possibility of a cyclical universe, where a big crunch leads not to an end, but to a rebound, a new big bang in an endless cycle of cosmic death and rebirth. This idea, sometimes called the conformal cyclic cosmology or a bouncing universe, suggests our universe is just one chapter in an infinite book, with each ending birthing a new beginning. The final chapter of cosmic history remains unwritten because we are still deciphering the nature of the dominant force writing it. We are like readers who have seen the first few sentences of the last page, but cannot make out the crucial words that determine how the story truly ends. Will it be a slow fade to black, a fiery collapse, a violent tear, or simply the turning of a page? The answer is hidden within the enigmatic push of the dark energy that fills the empty spaces between the stars. The profound silence of a universe filled only with light is a possibility we narrowly escaped. In the first, searing moments of the Big Bang, energy condensed into equal amounts of matter and its perfect mirror, antimatter. For every proton born, an antiproton was created. For every electron, a positron. These pairs are destined to annihilate upon contact, converting back into pure energy in a flash of gamma rays. If the universe had been perfectly symmetrical, this is exactly what should have happened. All the matter and all the antimatter would have found each other, mutually destructed, and left behind a cosmos of radiant, empty light, a universe with no stars, no planets, and no one to wonder about it. Yet here we are, made of matter, in a universe dominated by matter. This is not a minor detail, it is the central mystery of our existence, known as the Barrian asymmetry. For every billion particles of antimatter created in the Big Bang, there were 1,000,000,001 particles of matter. That 1 in a billion imbalance is all that remains. Everything we see is the ashes of that near-total annihilation, the leftover crumbs from a feast that almost consumed itself. To understand how this tiny surplus survived, we must delve into the fundamental rules of particle physics and find where those rules were broken. In the 1967, physicist Andrei Sakharov outlined the 3 necessary conditions for matter to win out. First, the universe had to be out of thermal equilibrium, meaning it was cooling and changing rapidly, not in a steady, even state. The Big Bang provided that chaos perfectly. Second, there had to be processes that did not conserve Barrian number, which is essentially a accounting of matter versus antimatter. Some interactions must have allowed matter to be created or destroyed in a net way. Theories like grand unification predict such processes where heavy, primordial particles decayed and tipped the scales. But the third condition is the most subtle and crucial, something called charge parity violation or CP violation. This is a crack in the mirror between matter and antimatter. It means that particles and their antiparticles should not just be mirror images in charge, but also in how they behave when their spatial coordinates are flipped, like looking at them in a mirror. If the laws of physics were perfectly symmetric under this combined CP operation, then matter and antimatter would behave identically, and any excess of one would be cancelled out. For matter to win, antimatter had to behave differently, even if just by a minuscule amount. The hunt for this tiny difference is the experimental quest to explain why we are here. In the 1960s, scientists studying the decay of neutral kaons, exotic subatomic particles, found the first evidence of CP violation. The decays of the kaon and its antimatter counterpart showed a slight but statistically significant difference. It was a monumental discovery, proving the symmetry was broken, but the effect was far too small to account for the vast cosmic imbalance we see. Today, the search continues at massive particle colliders like the Large Hadron Collider, focusing on another system, the beauty quarks and their antiparticles inside particles called B mesons. By creating billions of these particles and their antimatter twins and watching how they decay with exquisite precision, physicists are looking for any deviation, any hint that nature treats matter and antimatter differently in a way that could have seeded the early universe. They are essentially recreating, in a controlled detector, the conditions that might have tipped the first cosmic scales. Every atom in our bodies is a testament to a victory won in the first fraction of a second of time, a victory we do not yet understand. The known sources of CP violation in our best models are still insufficient, a whisper when we need a shout. This means our standard model of particle physics is incomplete. The true source of the asymmetry may lie in particles we have not yet discovered, like the heavy neutrinos predicted by grand unified theories or in the dynamics of the Higgs field. Some theories even suggest the imbalance was caused by processes in the very first moments of cosmic inflation, frozen into the fabric of the universe as it expanded exponentially. Solving the baryon asymmetry is not just an academic exercise, it is the search for our own origin story. It asks why there is something rather than nothing, and the answer will be written in the fragile, broken symmetry between a particle and its mirror. We are the evidence of that ancient breaking, living proof that the universe chose a side. Empty space can be terrifying in its scale. Nestled within the constellation Boötes lies not a brilliant cluster of galaxies, but its opposite, a staggering nothingness known as the Boötes void. This is one of the largest known structures in the entire observable universe, a spherical region of space roughly 330 million light-years across. To grasp that scale, if you placed our Milky Way galaxy at the center of this void, the nearest major galaxy would be so far away it would take a beam of light, traveling at the ultimate speed limit, millions of years just to reach the void's edge. This is not a simple gap between filaments in the cosmic web. It is a cavern of almost incomprehensible emptiness. The cosmic web, the large-scale structure of the universe, is supposed to look like a sponge, with dense filaments and clusters of galaxies surrounding vast but relatively modest bubble-like voids. These voids form naturally as gravity pulls matter into the filaments, leaving behind emptier regions. But the Boötes void is different. It is far too large and far too empty. When astronomers first mapped it in the 1980s, they expected to find thousands of galaxies lurking in its darkness. Instead, they have only confirmed a few dozen lonely island universes adrift in a sea of nothing. This presents a serious challenge to our models of how structure formed after the Big Bang. The problem is time. The universe is about 13.8 billion years old. That is a long time, but it is also a finite amount of time for gravity to do its work. For a void this colossal to have formed through the standard, gentle tug of gravitational attraction, the process would need to have started much earlier than our models allow. It is as if you walked into a forest and found a perfectly circular clearing 50 miles wide, with only a handful of trees in the entire area. Natural forest fires or storms could not create something so vast and clean. It defies the normal processes of growth and decay. The Boötes void presents a similar cosmic conundrum, dubbed the impossible void problem. How could something this empty get so big, so fast? Scientists are faced with two broad possibilities, each profound in its own way. The first is that we are simply witnessing a monumental statistical fluke. In a universe as vast as ours, even the most unlikely things must happen somewhere. Perhaps the Boötes void is that 1 in a trillion region where, by pure chance during the quantum fluctuations of the early universe, matter was distributed incredibly thinly. We just happen to be in a position to see it. In this view, the void is not impossible, just extraordinarily rare, a reminder that the cosmos can produce outliers that strain our sense of what is probable. The second possibility is that the void is a signpost for physics we do not yet understand. Could exotic forms of energy or interactions in the early universe have pushed matter away from this region more forcefully than gravity alone? Some speculative theories suggest that the repulsive force of dark energy might not be perfectly uniform, but could have had stronger, localized patches in the distant past, creating giant bubbles of repulsion that emptied out regions like Boötes. Others wonder if the void is evidence of a collision with another universe in the multiverse, a cosmic bruise where the structure was scraped away. While these ideas are far from mainstream, the very existence of the void forces cosmologists to check the foundations of their theories. Ultimately, the Boötes void is a lesson in humility written across hundreds of millions of light years. It shows us that the cosmic web is not just a delicate lace, but can have ragged, gaping holes whose origins we cannot yet fully explain. Whether a rare accident or a clue to new forces, this great nothing challenges our story of how everything came to be arranged. It asks us to look into the deepest emptiness and wonder what forces of creation or destruction once roared through that silent dark. A subtle bias in the molecules of life might have been delivered from the stars. Look at your own 2 hands. They are mirror images, identical in structure yet impossible to superimpose. This property, called chirality, exists at the most fundamental level of biology. Every protein in your body is built from amino acids, and on Earth, every single one of those amino acids used by life is left-handed. Their mirror twins, the right-handed versions, are utterly absent from our biological machinery. This is not a minor detail, it is a profound and universal rule for all known life on our planet. The mystery is why, in a purely chemical world, left and right-handed molecules should form in equal amounts. Any experiment that creates amino acids from scratch, like the classic Miller-Urey experiment that simulates early Earth conditions, produces a perfect 50-50 racemic mixture. Yet somehow, in the primordial soup where life first stirred, a decisive preference was established. Life chose a side, and it chose left. The answer to this biological puzzle may be written in the cosmos. In the late 1990s, scientists made a stunning discovery while studying the Murchison meteorite, a carbon-rich space rock that fell in Australia. This ancient fragment of the early solar system was loaded with amino acids, but they were not an even mix. The meteorite contained a significant excess of left-handed amino acids over right-handed ones. This was not life, it was a chemical fossil, proving that a chiral bias existed in space long before Earth formed. The building blocks of life arrived with a preference already stamped upon them. So what cosmic process could have imprinted this handedness on the raw materials of biology? One compelling theory points to the violent hearts of dead stars. Neutron stars, with their unimaginably powerful magnetic fields, emit not just light but intensely polarized light. This light twists in a specific direction as it travels through the vast clouds of interstellar dust and gas where complex molecules form. This circularly polarized radiation could have selectively destroyed one form of amino acid over the other, like a cosmic filter that only allows left-handed molecules to pass through and survive. Over millions of years, this process could have built up an excess in the molecular clouds that eventually collapsed to form our solar system. An even more fundamental possibility ties the bias to the very fabric of reality. The weak nuclear force, one of the 4 fundamental forces of nature, is itself chiral. It treats left and right-handed particles differently. This subtle asymmetry, buried deep within the laws of physics, could have influenced the way molecules formed and interacted in the early solar system. The radioactive decay of certain isotopes governed by the weak force emits electrons that are polarized. These electrons, interacting with precursor molecules in space or on the young Earth, could have provided the tiny nudge that tipped the scales toward left-handedness. This idea is breathtaking. It suggests the handedness of life is not a random accident of earthly chemistry, but a direct consequence of universal physics. If that is true, the implications are staggering. It means the preference for left-handed amino acids could be a galactic standard. On any distant world where life emerges from similar cosmic ingredients, it may very well be built from the same left-handed molecules. The proteins of an alien organism on a planet orbiting a star 100 light-years away could, in principle, be compatible with our own, a shared structural language dictated by the fundamental asymmetry of the universe. This mystery connects the microscopic machinery in our cells to the explosive deaths of stars and the deepest laws of particle physics. It tells us that life's blueprint may have been drafted in interstellar space long before our planet was born. The next time you look at your hands, remember that their asymmetry echoes a choice made in the cosmic dark, a choice that might be written into the very nature of reality itself. Our galaxy is not alone in the dark. Orbiting the Milky Way like cosmic fireflies are dozens of smaller, fainter collections of stars known as satellite galaxies. From the large and small Magellanic Clouds, visible to the naked eye in the southern hemisphere, to the faint, ghostly dwarfs like Draco and Sculptor, these celestial attendants are more than just neighbors. They are crucial tests for our most powerful theories of how the universe builds its structures, and according to those theories, something is deeply wrong with this picture. Our best supercomputer simulations of cosmic evolution, which follow the gravitational dance of dark matter from the Big Bang to the present day, paint a very specific forecast for a galaxy like ours. They predict that the Milky Way's immense halo of dark matter should have captured hundreds, even thousands, of these small satellite galaxies over its long history. These simulated dwarfs are not randomly scattered either. They should swarm around the Milky Way in a roughly spherical cloud, orbiting from all directions like bees around a hive. Yet when we look up, the reality is starkly different. Astronomers have only confirmed about 60 of these satellites, a mere fraction of the predicted multitude. This is the missing satellites problem. Where are all the small galaxies, and the ones we do see are not behaving? Instead of a spherical swarm, most of the Milky Way's brightest satellites are arranged in an astonishingly thin, rotating plane, a great disk of galaxies that circles our own like the rings of Saturn. This is the plane of satellites problem. Together, these two discrepancies form a serious crack in the foundation of galaxy formation theory. It suggests that either our simulations of dark matter are flawed, or our understanding of how stars form within these small halos is incomplete. One radical solution points to the very nature of dark matter itself. The standard model assumes dark matter is cold. This means its particles move slowly relative to the speed of light, allowing them to clump easily into the countless small, dense halos our simulations predict. But what if dark matter is warm? Warm dark matter particles would be lighter and faster, zipping through the early universe with enough energy to smooth out the smallest clumps. This would prevent hundreds of the tiniest dark matter halos from ever forming, neatly solving the missing satellites problem by ensuring they were never there to begin with. While attractive, this idea must also explain the strange plane of satellites we do see. Another possibility brings the violence of star formation to the forefront. In the early universe, the first stars to form in these small dwarf galaxies were monstrous and short-lived, exploding as supernova in a blink of cosmic time. These cataclysms could have blown out vast amounts of gas, stripping the small galaxies of the raw material needed to make more stars. Some may have been completely sterilized, leaving behind dark matter halos that are today utterly dark and invisible to our telescope's ghost galaxies of pure dark matter. This could explain why we see fewer luminous satellites than the simulations predict. As for the thin plane, it might be a fossil of a more dramatic past. Perhaps the Milky Way satellites did not form in place, but were acquired in a single, ancient collision with another galaxy. Such a merger could have torn a swarm of dwarf galaxies from the other galaxy and flung them into the peculiar, co-rotating disk we observe today, a celestial snapshot of a long-forgotten cosmic crash. The satellite galaxy problem forces us to look at our own galactic neighborhood with new, questioning eyes. Are we surrounded by a vast population of invisible dark matter ghosts, waiting to be detected by their gravitational pull alone? Or did the fiery births of the first stars reshape the cosmos in ways our cold simulations have missed? The answers are written in the faint, ancient light of these smallest galaxies, each one a surviving witness to a turbulent history we are only beginning to read. The cutting edge of astronomy is a place of constant surprise, where new instruments reveal cosmic phenomena so strange they have no name. This is the story of the odd radio circles, or ORC, a mystery so fresh its ink is still wet on the pages of discovery. In 2019, astronomers using the Australian Square Kilometre Array Pathfinder, a powerful radio telescope, were conducting a vast survey of the sky. As they sifted through the data, they spotted something impossible to ignore: faint, perfect circles of radio emission hanging in the dark. These were not the fuzzy blobs of distant galaxies, but crisp, ghostly rings like ripples frozen on a pond of space. Their sheer scale is what defies belief. A single ORC is so vast it could easily swallow an entire galaxy, spanning a distance that would take light hundreds of thousands of years to cross. Yet, when scientists pointed every other kind of telescope at these rings, they saw nothing. No optical light, no infrared glow, no X-ray signature. The circles were completely invisible to every eye except the radio one. They are cosmic phantoms etched onto the sky in a frequency only our most sensitive antennas can hear. The immediate question, of course, is what could possibly create such a structure. The rings are not solid objects, they are shells of emission, like the expanding blast wave from a colossal explosion. One leading theory imagines a cataclysm of almost unimaginable power, a merger between two supermassive black holes at the center of a galaxy. When such monsters finally spiral together, they can release a titanic burst of gravitational waves. That energy might propagate outward, shaking the thin gas between galaxies and creating a spherical shockwave that lights up in radio waves as it expands. We would be seeing the echo of a billion-year-old collision, a single, thunderous note still ringing across the cosmos. But there are other, far more exotic possibilities dancing at the edge of physics. Could an ORC be the throat of a wormhole, a tunnel through spacetime itself? In some theoretical models, the mouth of a traversable wormhole might be surrounded by a ring of hot plasma, held in place by immense gravitational and magnetic forces, potentially visible as a circle of radio emission. Or perhaps we are looking at the theoretical sphere of a rotating Kerr black hole, a region where spacetime is dragged around so violently it could produce observable rings of energy. These ideas venture into the realm of speculation, but they highlight just how alien these objects appear. They resist all our standard classifications. The true power of the odd radio circles lies not in any one explanation, but in what they represent. They are a direct message from the universe that our catalogue of celestial objects is incomplete. For decades, we have studied stars, galaxies, nebulae, and quasars, building a familiar cosmic zoo. The ORCs are a creature from outside that zoo, a shape we did not expect, found in a place we thought we understood. They remind us that every time we build a telescope with new sensitivity or a new view, we are essentially inventing a new sense with which to perceive the cosmos. And with that new sense, we often find that the universe has been doing things we never dreamed of, right in front of us, waiting for the right moment to be seen. The mystery of the ORCs is the mystery of discovery itself, the thrilling, humbling moment when we look at a perfectly clear signal and have to admit we have no idea what that is. These 25 cosmic mysteries are not dead ends but open doors. From the invisible architecture of dark matter to the phantom push of dark energy, from the silent question of the Fermi paradox to the screaming enigma of fast radio bursts, each puzzle is a frontier. They remind us that the universe is not a solved equation but a living story, and we have only just begun to read the first few pages. The great attractor pulls us, the pioneer anomaly teaches us humility, and the wow signal whispers of possibilities just beyond our hearing. The Kuiper belt cliff marks a boundary in our own backyard, while the axis of evil hints at a cosmos that is not as random as we thought. We grapple with missing lithium from the dawn of time and information that seems to vanish into black holes. Our own solar system tilts from an ancient encounter, while interstellar visitors like Oumuamua pass through like fleeting ghosts. The heart of our galaxy glows with a light that could be dark matter dying, and our most precise clocks measuring the universe's expansion stubbornly disagree. Mars breathes methane in cryptic puffs, and distant stars dim in ways that make us dream of alien engineers. We are searching for the quantum code of spacetime itself, dodging cosmic rays of impossible power, and wondering which of several profound fates, a freeze, a crunch, or a rip, awaits all of creation. We exist only because matter 101 in a billion battle against antimatter, a victory whose cause we still seek. We peer into impossible voids and find our galaxy surrounded by satellites that defy our best simulations, while strange new shapes, the odd radio circles, appear on maps where nothing should be. This is not a list of what we do not know, it is a map of where discovery is happening right now. Every mystery is an invitation to look deeper, think harder, and wonder more. So the next time you stand under a clear night sky, remember you are not just looking at points of light. You are gazing at the surface of a deep and turbulent ocean of questions, a cosmic horizon that recedes with every answer we find. Which of these mysteries captures your imagination the most? Let us know in the comments below. Subscribe to join us on more journeys to the edge of understanding, and never stop looking up with wonder.